Hi, everybody. This is Team Two's RC car final project for ME338. On our team, we have me, Jackson Fugia, Ryan Calcote, Andrew Wamba, Perry Scott, and Marco Figueroa. So I'm going to go through just a basic introduction first. What we did at the beginning was we decided to split the car up into three main components: the driving steering mechanism, the chassis body itself, and then the rear axle with the motor mount. Um, each of us will go through one of the parts and detailing our design goals, strategies, calculations, and simulations for it. And then at the end, we're going to talk about just the final assembly and how it all came to be. So Ryan's going to start talking about the chassis now.
All right, so our first choice with this was to 3D print the chassis because the ABS plastic would be lightweight. It would also give us a lot of flexibility in some of the more detailed design components. We chose a pretty basic rectangular body. We added slots running down the length of the body because our original goal when we were going to build this car in person was to use those slots to zip tie things like the battery down to the body instead of having to pin them in place. We also angled the tire wells to provide an improved range of motion. The next step that we did was to calculate like a reasonable impact force on the front of the car. So we decided the most likely time that our car would suffer a collision would be when it was turning a corner and hitting a wall. So we chose that to be at about half of the max velocity, so around 7 meters per second. And so we then needed to find the stiffness of the material since the impact force is a function of the velocity and the material stiffness. So we found the stiffness by running a displacement simulation in SolidWorks. And so then we were able to arrive at a displacement force of about 1,629 Newton seconds. So we figured this was a reasonable force to expect just because of the material that we chose and the desired speed. And we decided that the ABS plastic will withstand this force, that it was an acceptable number. So we moved on to the drivetrain after that.
I'll be talking about the drivetrain. So one of the main tenets of kind of our philosophy throughout this whole thing was to make everything as simple as possible. And so the first thing we did was try to do just a 1-to-1 simple gear ratio from the motor to the rear axle. And we wanted our top speed to be around 14 meters per second when we did our calculations, because we figured that if we had our calculations set to that high, then realistically it would operate between like 11 and 12 meters per second due to unaccounted friction, and that's kind of what we thought was reasonable. So as we are going throughout the 1-to-1 gear ratio, we realized that it just wasn't going to be feasible. The motor was going to spin the wheels too fast for it to make sense realistically. So we went back to the drawing board using this 1-to-3 gear ratio seen here. And in all of the calculations, you know, as you can see here, we just followed kind of the step-by-step procedure we did for the tests and homeworks and all that. And we got the axle torque to be around 29.66 millinewton meters, the motor torque to be 10.52 millinewton meters, which using the TS graph for the specific motor we have gave us around 21,000 RPM at the motor. So that gave us 7,000 RPM in the rear axle using the 3-to-1 ratio, which gave us a max velocity of 14.66 meters per second. This was above what we wanted, the 14 meters per second, but we didn't reiterate because, like we said, that number seems really high on paper, but realistically, it's not going to go that fast due to things like the ABS plastic causing unaccounted friction, the ball bearings messing up, things like that. So we just kind of kept it high on paper so that hopefully it'll be average in real life. And then just following the math, that gave us a average or a max acceleration of 16.48 meters per second squared at the stall torque of the motor. And then so once we had the drivetrain on paper, we 3D printed, or we modeled it in SolidWorks. And the way we connected it was, as you can see here, we mounted it above the rear axle using these two fins where we just slide the motor into place. And then we modeled the gears just as simple discs because we weren't too sure how to do a gear in SolidWorks, but this works well enough for our simulations. So that was kind of the extent of the drivetrain. And I think now that Andrew's going to talk about what we did with steering.
One thing to note about the rear axle is that the way that we catted it, there would be no way to actually assemble that if we printed those two pieces separately. So the solution to that would be split the axle into two pieces, so we could slip the axle through the holes in the back of the chassis and then super glue them into place, and then we could put the gear in the gear slot and then slip those two pieces into place for the sake of assembly.
Andrew, I think.
All right. Yeah. So for the steering design, this is one part of the project where we had a lot of options and different ideas. So we ended up going through a couple of sketches and deciding on this 4-bar steering mechanism that you can see that has the servo connected to a little servo arm that we ended up double layering for because it was a little bit weak at first. And that connects to the control bar, which you can see connects to both wheel bearings. We ended up choosing this one because it allows only a small difference between the angle of both wheels, and it actually allows the inner wheel to be turning at a higher angle, which you want for Ackerman's steering geometry, which is what cars and steering mechanisms rely on. So when you calculate the turning angle, you use the outer wheel because that's the minimum or the maximum turning radius. Sorry, minimum. And that came out to be 28 degrees, or 28 degrees gave us a radius of 18 inches, which when we considered like the track that's usually raced on, we figured that would be a like fine turning radius to get around the turns, even U-turning. And since this mechanism was actually the most complex of the three, we went through like a couple failed attempts before we decided to get to this one. And we're going to use these 1.5 inch number 8 32 3/4 threadless screws for the wheel bearings so that it can rotate with the servo. And if we physically had built the car, we would need to add some lubricant to reduce friction between the wheel mounts and the chassis, or maybe some ball bearings so that everything could rotate freely. And that's pretty much it.
Yeah, and then this was a simple video of just how it looked when you would rotate and kind of the game plan that was going to happen. This video doesn't have that second bar, but we added that to have some stability in there. All right, and then I think, Perry, you want to talk about just kind of how we assembled it all together at the end?
Yeah, sure. So after we completed the three main components, all we had to do was combine them all together, run our fatigue and stress simulations. Because we lacked some knowledge on things like zip ties and glue and tape. So we just used the mate method for SolidWorks to combine it all. So like the motor is mated, but that would be super glued. The battery, which is centered, we would use our slots to zip tie that down. So we also put the battery in the center of the chassis because that's probably one of the heavier components, and we wanted to maintain some balance. We don't have the motherboard and the receiver included in this, but those are like pretty light parts, so those would just be on either side of the battery, also for the sake of balance. We didn't know how to model bearings either, so where the bearings would be on the front axle is just where the wheels are mated to the steering mechanism, and then on the rear axle the bearings would be holding up the axle on the chassis. And that's pretty much it for the final assembly. So yeah,
and then one of the updated simulations we had was just to redo the force impact using our new steering design, and as you can see, it definitely would snap there. So in our final project and in the final report, we just haven't gotten to that step yet. We would change the material of that probably to be some kind of screw or steel so that it wouldn't snap as much given the force of the impact. And then I think that's about it for our video presentation. We were bummed that we had to do it this way, but I think that you can see we made the best of what we had and the way that this class works now. Thank you very much, and yeah.
thank you.